Hello everyone. In this video, we are going to talk about bipolar junction transistors. Let's start with explaining what the transistor is. Transistor is a semiconductor device, so that we can control or amplify the electrical signal by the transistors. So they are really valuable member of electronic world, and we use them for two main purposes. One is the amplifying the signal, and the other one is switching. Amplifying or amplifier is means that you can amplify the current voltage or power input, and the switching means that you can like turning on and off. It's like a switch, but in a high speed or high frequency. We use this application in digital electronic mostly. So let's see how the transistors are made. In order to make a transistor, you need this semiconductor material, because since it's a semiconductor device, we need the semiconductor material to build it. I think the first element comes into mind, as we say, semiconductor, is silicon. There are many transistors or diodes as well made by germanium, but we are going to stick to the silicon in this video. So, but there's a problem. The pure or intrinsic silicon is free of charge carriers. So we need to add some carriers into the silicon to use this as an active material. So it has a very low free electrons and holes, which are the charge carrier elements. So basically it acts as insulator. So in order to add a free charge carriers, we need to dope it. So we need to add some extra materials in the silicon. If we dope silicon with group 5A elements, such as nitrogen, phosphorus, arsenic, and so on and so forth, we can get an N-type semiconductor, which has an axis of electrons. Since the electrons, the polarity is negative. So from the N, we call this N-type semiconductor. And in N-type semiconductor, since we have the axis of electrons, the majority carriers are electrons. Due to the impurity, there are some carriers, there are some holes as well. Since the number of the holes are really less than the electrons, we call them the minority carriers. So the minority carriers are holes, and majority carriers are electrons in N-type semiconductor. Okay, so if we dope silicon with the 3A elements, such as boron, aluminum, and gallium, and so on and so forth, we will get a P-type semiconductor. Since the holes are positive, so from the P, we call them P-type semiconductor elements. So since we have axis of holes here, the majority carriers are holes, and also from the impurity, we also have some electrons, free electrons here. So they are the minority carriers in a P-type semiconductor. So when a P-type and an N-type semiconductor are joined together, a carrier-free region called the depletion region forms around the junction. So in this region, only ions remains, acceptors and donor ions. So it acts as an insulator barrier, and this also prevents the current flow under the equilibrium conditions. So if we arrange 3 layers of semiconductor materials in order of like N-type, P-type, and N-type, or P-type, N-type, and P-type, we create a transistor. So apparently transistor has 3 layers, and then it has 2 junctions, junction 1 and junction 2. So from this region we call emitter, and in middle region is base, and the last region is called collector. For an NPN transistor, the symbol is like this. and PN means NPN. So if the arrows pointing out, it's NPN. If the arrow pointing in, so this PNP transistor symbol. And also we have collector here, base here, and emitter here. So in order to, so if we look at the geometry, if we look at the structure based on the doping, so we have N++ here, P over here, and N+. So this plus means that the emitter region is heavily doped, and also this N+ means that the collector region is moderately doped, and this P, so there is no sign, which means that this base region is lightly doped. So to compare this, the emitter doping, the region of the emitter doping is higher than collector, and it's also higher than the base. So in terms of the surface area, so if you compare based on the surface area, we have collector. The collector is the region of the collector is higher or larger than ematter, and it's also larger than the base. We can compare this like this. So the reason why the collector is higher, because there will be the heat dissipation, and also it also gets rid of the voltage stress as well. And the reason why the base is too small, it's because there will be the carrier passing through this space. So the smaller the base is, the smaller chance to the carriers disappear here. So with the biasing of the transistor circuit, we could operate the transistor in 4 basic regions, which are the active region, saturation, cutoff, or inverse active region. So the active region is the place where, when we are biasing, if it works in the active region, that means that it works as an amplifier, current or voltage or power. Saturation means that, saturation and cutoff regions, we use them in digital electronics, or if we are going to use the transistor as the switch. So we have to use the transistor in saturation and cutoff. So the saturation will give us 1, or cutoff will give us 0, but not always, because it depends where you're taking the output is. The inverse active region, this is not really very common region, but it's worth to just mention it here. The reverse, in the inverse active, or we call this reverse active 2 region, the transistor still operates, but the current gain is very low, since the roles of emitter and collector are swapped. And so since the collector is not really sufficiently doped as emitter, so then the efficiency will be much less than the active region. Okay, so in order to operate the transistor in active region, we have to forward bias the junction 1, and the reverse bias the junction 2. I'm going to get into the forward or reverse bias in a minute. So for the saturation region, we have to forward bias the junction 1 and forward bias the junction 2. For the cutoff region, we have to reverse bias both of them. And for the inverse active, we have to reverse the biasing of the active, like junction 1 reverse biased and junction 2 forward biased. All right, so biasing unbiased PN. So if unbiasing PN junction means that if we do not apply any voltage to the PN junction, just the moderate size of depletion region forms, and apart from the random crossing of the carriers, so we do not see any current flows across the junction. So If we apply a voltage to the PN junction and in such a way that the positive end of the supply voltage comes to the P type, and the negative end of the power supply comes connected to the N type. So the holes, so in this case, the holes in the p-type region pushed towards the junction due to the same the repulsion of the same kind charges, because we have a plus here, and the holes are also positive, so they will just repel each other, and they will push the holes to the junction region. From the negative side, from the negative end, because of this minus, so the electrons, they will also push towards the junction. So for the result, the depletion region decrease, allowing the electrons flow from N-type region into the P-type region very easily. So for a negative reverse bias PN junction, if we reverse this signs from, so applying positive end to the N-type region and the negative end to the P-type region, so we will get a reversed bias. So the negative negative polarization over here will attract the holes which are positively charged. So they will attract the holes to this end and getting away from the depletion region. And the same thing happens here for the electrons and the plus end of the supply voltage. Then the electrons will be attracted to this end. And so this depletion region starts to increase, and then this, which forms a really high resistance to the electrons and the holes to cross the junction. So actually this junction becomes like an insulator. So if we, because in order to operate the transistor in active region, we have to forward bias the emitter, so junction 1, which is emitter and base regions, and we have to reverse bias the junction 2. So in this case, a large number of majority carriers, which are electrons from the emitters region, pass through the forward bias junction and diffuse across the reverse bias junction into the collector terminal. So here N represents the number of the electrons leaving the emitter side, and alpha means that represents the ratio of those electrons that successfully reach to the collector side. So since the N-type base terminal is very thin and has a low conductivity, a very small number of these carriers will take this path of a high resistance to the base terminal and generate the base current. And this is so that the base, this is why the magnitude of the base current is very small, which is typically on the order of microamperes. So in a reverse bias region, the junction creates a depletion region that prevents majority carriers from crossing. But however, since we have the minority carriers in base region, which are electrons, the minority carriers can still move across the junction because they are not repelled by the electric field. So therefore, a leakage current as we symbolize this ICBO, flows through the junction 2 and contribute to the also the IC current, which is the collector current. So one might think that how the carriers from emitter can pass through the reverse bias junction. I think the majority carriers from the emitter are the same type. So the majority carriers from the emitter part are the same type as the minority carriers in the base region. So when they enter the base region, actually they become minority carriers there. So since the minority carriers can move through the reverse bias junction, as we saw in ICBO case, these carriers continue to the collector, so they just pass easily, cross easily the I junction too. So this is why the current can still flow through the transistor, and even with one junction reversed biased. Okay, so talking about all the movements of the electrons, we create, the currents created. So we know that the current, the direction of the current is the opposite side of the direction of the electrons. So in this case, the movements of these electrons coming to the collector creates a collector current called IC, and also this the electrons leaving from the emitter creates a current with IE, we represent IE, and also the current leaving from the base, they create the current of base, which is IB. From the Kirchhoff, the nodal theorem states that, the total current entering a node, if you think that the transistor is a node, and so the total current entering to the transistor is equal to the total current leaving the transistor. So that will give us IE equal IB plus IC. From the current, from the collector current side, we can see that the electrons coming from the junction 1 and junction 2 is alpha times N and ICBO. So the collection of if we add them up, we will create IC. Here, N means that the electrons leaving from emitter, so which means it's just basically the emitter current, and then we can replace the N with IE, then our equation becomes like this. So ICBO, which is leaked current, so here C represents the collector, B is base, and O is open circuit. So this represents that this is the leakage current from a collector base junction, and it's when it's reversed biased. All right, this is all for this video. I'll see you in the next videos. Thank you so much for watching.